Okay, let's dive right in. We're going to explore one of the absolute biggest mysteries in all of physics, and we're going to do it by looking at a really powerful idea, the perfect mirror. See, at the very heart of our universe are these fundamental rules, things physicists call invariances. It's just this simple, elegant idea that the laws of physics should be the same for everyone, everywhere. It's like a perfect mirror, a description of how reality works that should look exactly the same no matter your perspective or how you twist it, turn it, or measure it. So on one side of this cosmic mirror, you've got matter, everything we see and touch, and its reflection, that's antimatter. It's identical in almost every way. Same mass, same spin, but some key properties, like its electrical charge, are flipped to their exact opposite. Now, our best theory of the universe, the Standard Model, is built on this very idea. It says this reflection must be a perfect mirror image. And right away, that leads to a huge, huge problem. Our theories are pretty clear that the Big Bang should have created matter and antimatter in perfectly equal amounts. If that happened, they should have immediately annihilated each other, leaving behind, well, nothing but a flash of energy. And yet, here we are. We live in a universe that is made almost entirely of matter. So the big question is, where did the reflection go? This is the central mystery that drives some of the most complex experiments on the entire planet.
To even begin to find an answer, scientists can't just go out and look for antimatter. It's just way too rare. They have to make it from scratch. And to do that, you have to go to a place that's one of a kind, CERN's Antimatter Factory.
The whole process is really one of extreme deceleration. You start by slamming high-energy protons into a target. Now get this, for every million protons you smash, you only get about 4 antiprotons that you can actually capture. These things are born incredibly hot, moving super fast. So they get corralled into this massive ring, the antiproton decelerator, which slams on the brakes, slowing them down until they're cool enough, we're talking just above absolute zero, to be caught in a magnetic bottle.
Now, because this process is so unbelievably difficult and energy intensive, it's led to this really popular claim you see all over the internet that antimatter is the most expensive substance on Earth. That price tag? A cool $62.5 trillion per gram. But is that really the right way to think about it?
The short answer, not really. I mean, that number is totally misleading. Nobody is buying or selling antimatter. In fact, at the rate we can make it now, it would take about 100 times billion years to produce a single gram. So here's the crucial point. The real value isn't in the antimatter itself. It's in the absolutely groundbreaking technologies that had to be invented just to study it. Things like medical PET scans and the super high vacuum tech that's used to make the microchips in your phone.
So with their homemade antimatter finally trapped and cooled, scientists can do what they set out to do. They can hold it up to that mirror of reality and look for the absolute tiniest crock, any little deviation at all that could explain why our matter-filled universe exists. Okay, first things first, the most fundamental question you can ask, and one that tests Einstein's theory of relativity itself. Does antimatter feel gravity the same way matter does, or, and this would be a shocker, could it fall up? To figure this out, the ALPHA-g experiment built this really slick, 3-meter-tall vertical trap. They create anti-hydrogen atoms and hold them inside this magnetic bottle. Then, very, very carefully, they weaken the magnetic fields at the top and the bottom, and they just watch. They count where the anti-atoms hit the wall and annihilate as they escape. It's a beautifully direct way to literally drop antimatter and see what gravity does. And the result, which was published in 2023, was a landmark moment for physics. Their measurement came out to about 0.75 G. Now, with the uncertainties of the experiment, that is perfectly consistent with the normal 1 G that you and I feel every day. Repulsive anti-gravity was officially ruled out. The mirror holds, antimatter falls down. Okay, so it falls the same way. But is its internal structure the same? To test this, scientists look at its color. Now, they don't mean color like red or blue, they mean its energy spectrum. They zap the anti-atoms with lasers and measure the exact frequency of light they absorb. Any difference at all compared to regular hydrogen would be a crack in that mirror. And the precision they achieved here is just astounding. They measured a key energy transition in anti-hydrogen and found that it matches regular hydrogen perfectly, down to 2 parts per trillion. To put that in perspective, that's like measuring the distance from the Earth to the Sun and being accurate to within the width of a single human hair. As far as we can tell, the reflection is absolutely flawless.
And you know how they pulled this off? A massive leap in efficiency. They got so much better at creating and studying these antiatoms that a measurement that used to take 10 weeks of painstaking work can now be done in a single day. That's a total game changer for pushing the boundaries of what's possible. But what if you want to measure the exact value of gravity's pull? Well, for that, another experiment, called AEgIS, needed a detector with microscopic precision to see the tiny, tiny drop of a beam of antiatoms. And the solution they found didn't come from some specialized physics lab. It came from a completely unexpected place.
Yeah, believe it or not, the answer was found in the exact same kind of technology that powers the camera in your smartphone.
The engineering here is just so clever. It's basically a scientific hack. To create what they call the OPFNIM detector, scientists took 60 off-the-shelf camera sensors, physically and chemically stripped away all their color filters and protective layers, and then stitched them all together. What they ended up with is the highest resolution particle detector ever built. It can pinpoint an antimatter annihilation event with sub-micron accuracy, and it does it in real time. Just incredible.
So, after all of these incredible experiments, weighing antimatter, checking its color, measuring its magnetism, what's the final verdict? What's the state of the mirror of reality? Well, the verdict is in, and as far as we can possibly tell, the mirror is flawless. Every single property of antimatter that we have managed to measure so far is a perfect symmetrical reflection of matter. The fundamental laws of physics appear to be perfectly balanced. And this is so important to understand. Even though no crack in the mirror has been found, these results are not failures. Far from it. They are staggering triumphs of engineering and precision. They push the absolute limits of what humanity is capable of measuring. And you know what? Each time they find nothing, it just makes the original mystery that much deeper. Which brings us right back to that ultimate question. If the symmetry between matter and its reflection is so perfect, if the laws of physics are this balanced, then why did one survive the Big Bang and the other just vanish? The mirror is unbroken, but half the image is missing. And that remains one of the greatest unsolved puzzles in all of science.